Okay, everybody, continuing on with Chapter 4, Exponential and Logarithmic Functions. Looking at logarithmic functions first. We're going to take a look at those, graphs of them, the common logs, and the natural logs. So here, every exponential function of f of x equals a to the x, with a is greater than 0, and of course not equal to 1, is a one-to-one function by the horizontal line test. Now, of course, you have to do the vertical line test first to make sure it is a function before you can do the horizontal line test. They're assuming that you did that in that statement. The inverse function is called the logarithmic function with the base a and is denoted by log base a. And we're going to recall that f of -1 is defined by the inverse. F of x equals y, so f of y will be equal to x. And this will lead to the following definition. If we have log base a of x equals y, you can see that that is, or a to the y is then going to equal x. So again, if you have a to the y equals x, that'll take it from log form to exponential form. And we can take a look at switching these. Here we have 10 to the 5th equals 100,000. 2 to the 3rd equals 8. 2 to the -3 would be equal to 1/8. And 5 to the r would be equal to s. So it's important to understand that this in itself is an exponent. So the number in the right column of the margins are the logarithms, base 10 of the numbers in the left column. This is the case for all bases, as the following example will illustrate here. Again, 10 to the 3rd equals 1,000. 2 to the 5th will equal 32. 10 to the -1 is equal to 1/10. And 16 to the 1/2 is equal to 4. Now we have some properties, and you will see that these match up with our exponential properties that we looked at before. If I have a to the 0, that's equal to 1. If I have a to the 1st, that's equal to a. If I have a to the x, that's equal to a to the x. And since these are inverses of each other, then if you take a to the log base ax, you will get x. Okay, so now I am not going to require that you know what property to use. I just want you to understand and be able to use the properties. Let's take a look at the graph. Now, if we have a one-to-one function, it has a domain A and a range of B. Its inverse will have a domain B and a range A. So since the exponential function f of x equals a to the x, of course a is not equal to 1, has the domain of real numbers in the range of 0 to infinity, we can include that its inverse has the reverse. That means that it will be reflected about our parent linear function y equals x. Here we go. Here's our exponential function here that we looked at before. Notice that it goes through 1 on the y-axis. So the logarithm, which is its inverse, is going to go through 1 on the x-axis. Okay, so again, the fact that y equals a to the x for a is greater than 1 is very rapidly increasing, implies that y equals log a to the x is very slowly increasing for x is greater than 1. Now, since we have log base a 1 equals 0, the x-intercept is of the function log base a of x is going to be 1. So before the y-intercept was 1, and now the x-intercept is 1. So the y-axis is vertical asymptote of y equals log base a to the x because log base a to the x is equal to negative infinity as x approaches 0 from the positive side. That's what this means, remember, from the positive side. So now let's sketch the graph. Here we can plug in numbers and we can see that as we come up here, we're going to go through 1 and then again come this way. And we want to take a look at, here's 10, 5, 3, and 2. Now before we were saying that the larger the base, the steeper the slope. Well, that still can be the case to take a look at as long as you are measuring the slope right here. Okay, so you can see how steep this comes up right here, right here, and then it's a little less steep, and a little less steep, and then a little less steep. So you can still use that as long as you remember to look at this area, because once you get past the x-intercept, it gets to be a less steep slope for the higher. So whichever way you want to remember it, you can say, well, since it's the inverse, it's the reverse of what we did before, or you can look over here before you hit the x-intercept. So these graphs are drawn by reflecting the graphs about the line y equals x. So let's take a look at sketching the graph. Notice the first one is showing you the reflection of the whole thing is negative, and the second one is when we're going to reflect the x first. Here we have our going through our x-axis, and then if I'm going to reflect it about the x-axis, and it'll look this way. And that's what happens when I take the negative value of the whole thing. If I'm going to take the negative value of the x, it'll go through the value of 1 on the x-axis, and then it will go through the value of negative 1 on the x-axis, so it reflects about the y. It spins around the y-axis right here. So look at common logs. The only difference between a common log is its base. Similarly to when we have square root, we don't put the 2. If we have a common base log, we don't put the 10. So it's similar to that. So this is really down here. This would actually be 10 to the first power is equal to 10. But since it's so common, we don't put the 10. So anytime there is not a number down here, you can assume that that number is 10. Just like when we have a square root, you can assume the number is 2. So here this is 10 to the second power is equal to 100. So how do we find log of 50? We need to find the exponent such that 10 to the whatever power is equal to 50. And that's where our calculator will come in handy. Okay, so we can see that in this one, our graph 1 is going to be too small because 10 to the first is just 10, and 10 to the second is 100. So we want to find a number that's between 1 and 2 that'll give us 10 to the 50. So we can find this by using our log button on our calculator. Okay, so the calculator will find the approximate value for the log of x, which again, anytime you don't see a base here, it's 10. So we make a table of values and we can examine it closely here. Now, scientists model human responses to stimuli such as sound, light, pressure using log functions. For example, the intensity of a sound must be increased manyfold before we feel the loudness has simply doubled. So the psychologist, again, anytime somebody discovers something, we are going to give them the credit. Gustav Fechner formulated the law as this, where S is the subjective intensity of the stimulus, I is the physical intensity of the stimulus, and L sub 0 stands for the threshold of physical intensity. K would be the constant that is different than each sensory stimulus. So the perception of the loudness, which is B, which is decimals, and decimals would be dB of a sound, of physical intensity, would be given by this formula, where L sub O is the physical intensity of barely audible sound, and the decimal level of the loudness of a sound whose physical intensity of L is 100 times that of L sub 0. Now we'll find the decimals of the level B by using the fact that I equals 100 times L sub 0. Okay, so here we have our 10 log of 100 I sub 0 over I sub 0, and we know that this means that these two will reduce. They're going to say cancel, and that's going to drive me crazy, but we're reducing. So now we have 10 log base 10 of 100, and we know that log base 10 of 100 is equal to 2. So the loudness would be 20 decimals. Now, natural logs, the difference here is that the natural log was going to be log base E. All the same properties will still apply. Here we again have the inverse function, but this time instead of using the word log, we use ln. And anytime you see ln, that means that it is log base E. So again, I want to emphasize that ln, oh, it wasn't letting me write, and then it just went crazy there. So let's get rid of that, and let's take a look at log base E is actually equal to ln. Okay, so these are the same. So log base E means ln. Properties are exactly the same. Remember, there's a little e right here. It's a log base E, so e to the 0 is 1, e to the first is e to the x is e to the x, and these will be inverses of each other, so we'll just have x. Here's some examples. E to the 8 is equal to e to the 8. You can use your calculator key. Okay, so finding the domain of the function, we're going to want to take a look at the inside here. We have 4 minus x squared. We know it's only defined when x is greater than 0. So we have to take this and set it greater than 0. And when we solve that, we will get x squared is less than 4. If I continue to solve it, that means the absolute value is going to be less than 2, and that'll give me the range here between -2 and +2 for my x values for my domain. All right, well, that is it for section 4.3, and we'll be heading on to section 4.4.